Okay. Hopefully at least some of the remaining 8 people will show up. So with problem set 4 coming up due on Monday, but anytime on Monday, so for you guys effectively Monday night or Tuesday morning, make sure to bring your questions about that to class on Monday. Now the main purpose of Monday will be review for a test, but that's also what's on tap for today too. Okay. And then I'll have problem set 3 back to you by then also. There's one example I didn't get around to from exact equations from last time, so I'm going to do that now. And this question came up last time, and since I don't pay much attention to the textbook because most textbooks are awful, the actual coverage of a test will be 2.1 to 2.3, skip 2.4, and then 2526. There's other stuff in chapter 2 later that either won't be on a test or actually won't be on any test or not covered at all. So that's it. And exact equations, where we were on Wednesday, that is 2.6. Okay. So this example, so how, since these equations can be written in different ways, you see this from problems in the textbook also. This is the most common way in which these types of problems are written. Something times dx plus something times dy is equal to 0. And this problem has an initial condition that we'll take into account at the end. Also, it's important to be aware of what form of problem it's in and make sure that it's in the right form to actually work with. And it's in that form right now. It could have been written something like y prime is equal to y minus 2x over 2y minus x. So where I move this to the other side. So like some of the problems in homework are phrased this way, and your first order of business, get it in this form. Keeping in mind, of course, that y prime is dy dx. And although it gets everything that you saw from calculus, we're actually able to split this into numerator and denominator and move them around. Okay. But now that this equation is in the right form, you need to identify your coefficients. So this is capital M of xy. Whatever's multiplying the dx is your capital M. Students get thrown off too easily if things are written slightly differently, which is why I'm focusing on this now. Whatever's multiplying the dx is your m. Whatever's multiplying the dy is your n. Make sure everything's on one side, set equal to 0. Okay. So now what you do is your check for exactness. And that check is the partial derivative with respect to y, also known as m sub y, is that equal to nx, so partial of n with respect to x. I'm using both notations, I don't care which one you use, but I want you to be accustomed to both. So, what do we have for derivative of m with respect to y? Yeah. And then nx, also negative 1. Yeah. So this one checks out, it's exact. If it had not been exact, then we would do, like I showed you last time, try to find an integrating factor. That's a very strange looking check mark. Okay. So now, this is the case we like to have. So now we can go ahead and solve by integration. So first thing we do, so function f of xy is going to implicitly describe a solution for us is going to be an integral, so an antiderivative of m with respect to x. So we'll fill in what m is. Okay, 2x minus y. Okay. And what do we have for that?
X squared minus yx.
Yeah. Okay. Plus what?
Plus c.
Not c.
No.
What?
C of x.
Yeah, the function of y. Since we are integrating with respect to x, whatever you add on must be independent of whatever variable integrated with respect to. So I'll call this unknown function g of y. Okay. That way, if you were to go backwards, differentiate this with respect to x, the point is this goes away, and you recover this. Okay, questions so far? All right. Now, the g of y satisfies this equation, where we take our n from up here, subtract off a derivative of what we got by integration. Plus. And in my notes, I've referred to this as m1. So this is derivative of, I'll write it that way. Whoa, that's awful. I'm afraid I want to fit everything I do in a day into one board. Okay. You can just take pictures and zoom in. All right. So whatever you got by integration, differentiate that with respect to y, and you subtract it off. So n is 2y minus x. And then derivative of this with respect to y is what? Almost. Yeah, negative x. Okay. All right, and so we have a minus x and a plus x here. The x's are going to cancel. That's something that's typical of these problems. So in this case, what's left over cannot depend on x. If it does, you made a mistake somewhere. So we get 2y. So to summarize, g prime of y. Oh, I totally forgot to write that. Well, okay. To fix your notes, g prime of y is supposed to equal all of this. Okay. All right. So the g prime of y, which, to be clear, is n minus partial of n1 with respect to y, is equal to 2y. So okay. So g of y is what? Yeah, y squared. And here we add on a constant. All right. Okay, so these are our two crucial pieces right here. Okay. Now,
So what is that connected to? The last thing we just did?
this,
Yeah.
that gives us this. So big F is what we're looking for because it describes our solution. We got all of it earlier except this piece, and now we have it. Okay.
Where did the negative x come from?
This? Okay, so n this is n. And then I took what I got earlier, which I've labeled m1, and take a derivative of that in respect to y.
Oh.
And that gets subtracted off. You have a question?
So this is this is g of y. This is g of y or g prime of y.
G prime equals this. That's what I have here.
Okay.
Thus, we solve for g of y by integration. Is there a question, please? Okay.
I want you on this one.
All right.
I want you on this.
Now we can put all the pieces together. So the solution y satisfies equation big F of xy is equal to 0, where big F is equal to m1 that we got by our first integration, x squared minus yx, plus the g of y we were just finding, so x squared minus yx plus, and g of y turned out to be y squared plus c. Right. So this is our big F that characterizes the solution. So the implicit solution is this equation, x squared minus, actually starting let's write yx, I'm going to write xy, plus y squared plus c is equal to 0. But this is the general solution. In other words, any solution of this differential equation has this form. But we still have the initial condition to take into account. But before we handle that, any questions up to this point? Okay. So, for initial condition, says that y of 1 is equal to 3. So what we do is we set x equal 1 and y equals 3 in this equation. And we use that to solve for c. So we have 1 minus 3 plus 9 plus c is equal to 0. So what is c? Yeah. Okay, so now we have an implicit description of our solution that satisfies the initial condition. So we have x squared minus xy plus y squared, and then we throw in the minus 7 is equal to 0. All right. Now, in many cases, we could stop here, or we have to stop here. In this case, we don't, because if we look at the dependence on y, we have a y squared, and then we have something times y, and then the rest of it doesn't depend on y at all. This is a quadratic equation in y. So we can use a quadratic formula to solve for y explicitly. So think of ay squared plus by plus c is 0. So our a is 1, and then our b is whatever's multiplying y, which is minus x. And then our c is everything that doesn't include y at all. So that would be x squared minus 7. So now we can go ahead and apply the quadratic formula. So solving for y, so what would that be? Yeah, so fill in the blanks.
X plus or minus square root of x squared minus 4 times 1 times x minus square root minus 7 over 2.
Okay. All right. Okay, we simplify this to x plus or minus. Okay, so we have x squared minus 4x squared, and then we have minus 4 times minus 7, so 28 minus 3x squared all over 2. Okay. This problem is supposed to have a unique solution. We have 2. Plus or minus, how do we choose?
You have to use the initial condition.
Use the initial condition again. So we go ahead and set x equal to 1. Then we must get a result of 3. So x equals 1, we get 3 is supposed to equal 1 plus or minus square root of 28 minus 3 all over 2. So we get 1 plus or minus 5 over 2. So it's the plus sign that gives us a correct result. So that is our final answer. Y is equal to x plus square root of 28 minus 3x squared all over 2.
Wait, how did you get the plus?
Because, all right, are you good down to here? Okay. Well, if I chose the minus, I would get whatever I get here must be equal to 3. But if I choose a minus, I'm going to get minus 2. So these problems, once you have an initial condition, they must have one solution. So in a case like this, where you have a y squared, you can solve by quadratic formula. Only one of those signs is going to satisfy the initial condition. Unless you're lucky and this turns out to be 0, then you're good. Any other questions? All right. So now that we've seen another example of exact equations, I have another test simulation for you. And actually, while I hand these around, I'm also going to hand around the attendance sheet. I actually remember today. And this one's going to be on the latest material. Actually, let me take half that step. As you get it, take a look at the first sheet that basically reviews what we saw just now, and also what to do with the integrating factor. So, first problem, you're going to be walked through the process. It's going to ask you for certain things along the way. You fill in those steps, and then we'll see how much progress you can make in a short amount of time. Does everybody have one? Okay. All right. Let me get the stopwatch over here. Okay. you have, on a real test, you have 7 required problems, so it's about 7 minutes per problem. So let's see what you can do in 7 minutes. Go. and stop. Now, I was just thinking, like, now that I take a little time to do this, and you guys are working while I'm just waiting, I get to experience what you guys do routinely, being bored in the middle of class. Did anyone, we're going to correct this now, we'll check correctness in a moment. Did anyone get to produce a solution? Anyone? What about this stage, at least getting a new equation? Now, as I said, like, you a test, about average 7 minutes. Now, this problem will be when it's not exact, so you need an integrating factor. This would require probably above average amount of time. But what I really want to see is, since we're going to do a second problem in a moment, can you at least do better than you got here? Did anyone produce an integrating factor at least? Okay, well, I should mention that my tests actually have fewer problems on it than that some other instructors do for 50 minutes. But let's see. Well, I do want to collect these at the end, and I'll see how far, in an average sense, people got. So first, getting equations just in the right form. That's why I was harping on this earlier in anticipation of this. Because the equation, your m should be e to the 2x plus y minus 1. And then n would then be minus 1. Now, if you have the same things but both are the opposite sign, that's also valid. Because the whole equation is set equal to 0. So this is just from rearranging, because I had dy dx equals something. So the first order of business is you can multiply through by dx and then put everything onto one side.
Why would n be a negative 1? Was it?
Because what happens is, so after multiplying through by dx, what you have is dy is all of that. And then, now, okay, so you have a choice. You can either move this to the other side or move this to the other side.
How is that whole thing m?
Well, it's whatever's multiplying dx. Because what's written is dy dx equals this. I just multiplied both sides by dx. So your equation is in this form. M dx plus n dy is 0.
So I don't understand how you got that the positive 1. I'm sorry, negative 1.
We had to move the dy. You had to move the dy to the other side.
Yeah.
Leaving that side equal to 0.
Okay.
Yeah. So, I either had to move this over there or this over here. Something's getting negated. And then you take the derivatives. Well, this one, of course, is going to be 0 because that's a constant. And then derivative this with respect to y is going to be 1. So these don't match. So now you need to make sure that either this depends only on x or this depends only on y. So if you do, your numerator is going to be 1 in this case or minus 1 in this case. So n is minus 1, and then here we have e to the 2x plus y minus 1. So this is the one that works out. That this equation at least doesn't depend on y. I mean, it's certainly perfectly fine to be a constant. That's actually preferable. So now, to get mu, we have mu prime of x is equal to this quantity, minus 1, times mu. So what is mu? We've seen a lot of these integrating factor equations. They all work out the same way. How's it start? Mu equals
E to
e.
the integral of p dt.
Yeah, so the integral of this, whatever's multiplying it. So it's e to the minus x. Then what happens is So your old equation was e to the 2x plus y minus 1 dx minus dy is 0. Now you multiply both sides of this by e to the minus x, and what you get is a new equation. So e to the x plus y minus 1 e to the minus x dx minus e to the minus x dy equals 0. So this is your new m, and this is your new n. And if you were to take derivatives of this with respect to y and this with respect to x, that would turn out to be, they would match. And if time permits, that's something you want to check. And then you can solve for this by integration. So your big F is going to be the integral of m with respect to x. So we're going to get e to the x minus x plus some unknown function of y. So this right here is the integral of your new m with respect to x. And then g prime is equal to n minus partial of all this with respect to y, and your new n is minus e to the minus x, and then a derivative of all this with respect to y. This is the only y dependence, and you get okay. Because all of that works out to be 0. Okay. Sorry, something strange is going on in my notes, or now it's my turn to lose my mind. Okay. Now we have, based on my notes, and my knowledge of solution is supposed to be 0. Okay, so so therefore, g of y is just a constant. Call it c. So now your solution is e to the x minus y minus 1 e to the minus x plus c is equal to 0. That's your final answer. Okay. Alrighty. Okay. Yes.
Can you not separate that equation in terms of x and y and do the integral in the very first place? The original equation on top.
Okay. Where do?
Can we not separate that in terms of x and y and do the integral?
Oh, you mean like a separable equation?
Yes.
Because you can't write it as a product of function of x times a function of y. It's all you have here is a sum of those kind of functions. It has to be a product. So no, this equation is not separable. Any other question?
I'm just confused right there. At the bottom.
Yeah.
No. The e to the x.
Well, here I have e to the minus x times e to the 2x. I add the exponents.
I'm saying, why are you doing that?
Oh, because This is our original equation.
Mm-hmm.
To make it exact, I multiply through by the integrating factor. So I'm multiplying everything by this e to the minus x. And that will produce a new m, new n, that satisfy the condition for exactness.
And you took that for the integrating factor. You took that -1 from x right there, correct?
Or
Yeah.
yes.
Okay.
Yeah, that goes down here.
Okay. Originally, I thought that you had like taken it from that equation up there.
Oh, no. Yeah, one of these will produce your equation integrating factor. Okay. Any other question? Yes.
So you just take M and then add G with Y to it.
Well, what happens is I take my m and I integrate it with respect to x. Yeah, then I add g to it. This equation can be solved explicitly for y. If I multiply both sides by e to the x, I have e to the 2x minus y minus 1 plus c e to the x equals 0. So then I can say y, I can move this y to the other side, and I get e to the 2x plus 1 plus c e to the x equals 0. So that's a solution in explicit form, but that's not always possible. Okay. Yes?
I just want to make sure. So when you multiply them with your integrating factor, you always use your original equation.
You always what?
You use your original equation.
Right. Yeah, because once you get to the integrating factor, you go back to that and scale it. Okay. Do we have time for one more question? Okay. You have another problem on the last page. Give it a go. Follow the same schematic, it's just not written there. Here's some trig reminders for you. and stop. We only have 2 minutes left. Run down this. Your m is just the e to the x, the first term. So m1. Your n is everything that's multiplying y prime. So then differentiate respect to and y is 0, and x is going to be e to the x cotangent y, so they're certainly not equal. And then the one that's going to pan out is going to be this one, because you get nx minus my, that's e to the x cotangent y over e to the x, so the e to the x's cancel. So your equation for integrating factors, mu prime is equal to cotangent y times mu. Mu is a function of y. So mu is of y is e to the integral of cotangent is cosine over sine. So this is a rather unusual integrating factor, but one that does simplify a lot. So that integral, well, how do you simplify that integral? Substitution. Yeah, let u be equal to sine. So then du is cosine. So you're integrating 1 over u du. So it's e to the log sine, which simplifies to just sine. So sine is your integrating factor. So now your new equation is e to the x sine y dx plus e to the x cosine y plus 2y dy is 0. Therefore, your f is the integral of this with respect to x, which is just e to the x sine y itself, and almost integrated with respect to y. And then when you work out this part to get your g of y, you end up just getting y squared. So that ends up being your solution in implicit form. It's not possible to solve for y in this case. So if you, so again, for a test, speed is important. You're seeing steps. Hopefully you got through it a second time or the first time. But some other problems that might be easier, like a separable linear equation, get those out of the way quickly so you can spend more time on this if you need to. I do want to collect those, and I will give feedback on Monday. Yes?
I would like to if I put my name on it,
Yeah, go ahead. If you want feedback, go put your name on it. But I want to collect those whether your name's on it or not.